So welcome. I'm Roberto. This is Life of an Erlang process. I'm a software engineer. I'm a Erlang passionate. I've been working with Erlang for about 8 years now. I'm Sicilian, but I'm based in Stockholm, Sweden. This is the secret plan of conquering the world by Erlang Solutions, which is the company I work for. This is the current expansion map. The only reason why I'm showing this is because we are hiring. We look for Erlang developers or people interested in functional programming. So if you're interested and you want to move to one of the red countries, just talk to me after the talk. We also have a few others, like US. But we're not here about talking about myself or Erlang Solutions, so let's talk about Erlang instead. And there is a very big disclaimer I need to make, which is I won't be talking about Erlang syntax at all, or kind of. And the real reason is because I strongly believe that syntax is actually irrelevant. What is not irrelevant is a programming language that you're using. So, of course, if you have a nicer syntax, it's much better. It's a pleasure to use rather than using an ugly syntax. But it doesn't really matter if the syntax is nice or bad. What really matters is the concepts and the principles which are behind the programming language that you're using. Does the programming language you're using allow you to express in a way that allows you to solve problems in a certain way? Can you be productive while using that language? The fact that Erlang has a horrible syntax might play a bit of a role in there, but if I explain you the concepts, my hope is that when you will discover the syntax, will be already too late, because you will love so much the language that you actually want to use it despite of the syntax. And if you're interested in the syntax, there is a workshop as well, which is simultaneous to this one. So you can go there instead. Okay, so, but Erlang, like mandatory introduction, it's been around for a while, more than 20 years now. It's been developed at Ericsson in Sweden. Has been originally created for telecommunications problems, and then they realized that the problems they were trying to solve were actually common to many other scenarios. So this is why they started to become more and more popular, and they finally open sourced the language. So Erlang is a language which has been created for helping developers, the developers within Ericsson, to build scalable systems, which are, I'm not going to talk too much about this, but I need to give you like an introduction. So you want to use Erlang for providing a scalable, a fault-tolerant, a highly available, massively concurrent, distributed, soft real-time system, which is like Erlang all the things. I don't care, like you can read about this stuff yourself. There are books, there are blogs, whatever. The only thing you need to, I would like you to remember after this talk is the main idea which is behind Erlang, which is we want to write a scalable system. So this is the main concept. You want to write a scalable system. Having a scalable system means possibly having tons of users. Hundreds of thousands, millions of users, because otherwise you don't really need a scalable system in the first place. If you are in that scenario, well, what you want to do with Erlang is to model each user as a process, which hopefully means that you will have to deal with tons of processes. And this is not just theory, it happens in practice. WhatsApp is implemented in Erlang, is one of the notorious examples. Their team is like 32 engineers. They've been bought by Facebook for a ridiculously high amount of money, not just for the software, but because of the users they had. And they actually managed to do this with Erlang. So it's a quite exotic language. It's functional. But it doesn't really matter it's functional, it happens to be functional. The main problem, the main point about Erlang is that Erlang is a concurrent language. So that's what you need to focus on. It's not the fact there is actually, yeah, it's a functional language, it has a couple of nice properties. The fact that it's functional is because having a functional programming language helps implementing a concurrent language. So the only thing you need to remember after this talk is every time you think about Erlang, don't think about syntax, don't think about anything else, just think about processes. And hopefully you will deal with a lot of processes. So how do you do that? How do you deal with a lot of processes? Well, processes need to be extremely cheap to create. If you want to model every user or every action of a user, in WhatsApp, they model like a message. When you send a message, that's a new process which is created in your system. And you can just think how many concurrent processes you can have in the WhatsApp backends, because, well, think about how many WhatsApp users you have and how many messages they exchange at any given time. So you want processes which are extremely cheap to create because you need to create them on demand. You also need to be extremely fast when you context switch between one process and the other. Otherwise, this is just not feasible. So using something like an operating system process is out of discussion. You can't do that. It's too expensive. And the same applies for operating system threads. That would be too much. You need something more lightweight. And what we have in Erlang is lightweight processes. If you reason in this way, what you will end up is with, like, say, a machine where you start creating tons of processes. But at some point, you will reach a limit. So the hardware will not allow you to create. It doesn't matter if they are cheap to create. At some point, you will reach like the limit for creating process on a single system. So what you want to do is to be able to create these processes remotely on other machines. You want to horizontally scale. You want to throw cheap hardware into your existing system, and you want these systems to communicate together. You want to be completely transparent when you create a process, if the process is local or remote. And Erlang has this as built-in support for distribution. There is also, if you want to write and implement a scalable system, you want to do something else. You want to think about shared memories. Like, if you follow the keynote, there was this concept of, yeah, we have these functions, and then we create this global variable. We have an entry point which is accessed by several different, let's call them clients. This is a bottleneck. This is a scalability issue. You don't want things like shared memory. Because if you have a scalable system, what happens is that if you have, imagine this massively scalable system, distributed, having a restart in one of the components, having a crash will be perfectly normal. And if you have the concept of shared memory, so like portion, like some resource which is accessed concurrently by several clients at the same time, in case of a crash or a restart, which is normal at this scale, you will leave the system in an inconsistent state, and it will be extremely painful to recover and bring the system back to a consistent state. So we need to think about how to avoid shared memory. And the way this works in Erlang is, for example, by using message passing. So we have a lot of processes which communicate by sending messages between each other. All the messages are copied, which of course means it's slower, but it's safer. And if you're at this scale, you need to live with this. Of course, you can't have anything. I'm not here to tell you Erlang will solve all the problems you have, or whatever you have done so far doesn't apply to Erlang. That's just wrong. So if you are at the system at a huge scale with a lot of restarts and crashes, the other main principle that you need to follow is to fail fast. And this has been mentioned in many other conferences. Now people are grasping this concept more and more. The idea here is that if you're at this scale, you will have a fault. And false errors are everywhere. You cannot prevent them. You cannot write a system without thinking about faults. So what you do instead is, well, you report somehow the failure that you have, and then die. Try to not to propagate your error like to your neighbors. So Erlang doesn't have a static type system. This can bring, of course, to errors. Because, well, if you don't have a static type system, if you attended the type talk, it's easy like to make type mistakes, and then you will realize that you made a mistake at runtime. But is that really important? Because if you have a way to just fail and then recover from that situation, well, it doesn't really matter. If you have a dynamic like typed language, you can write your code in a more dynamic way. You have nice features like hot code swapping, which are not available in other systems. But then, if you follow this principle, like errors will happen. Doesn't matter. So just report the failure and die as soon as possible. So this was very general. I hope that the main point was, please think about processes, and processes are a good thing for you. So now we should go a bit more in detail. So what's a process? This is a process. Process is a circle, is a ball with, this is how you find it in books, slides, training material, everywhere. And it has this little thing, which we call the process identifier. It's an identifier for the process. In this case, this is process number 42. Occasionally in Erlang you can also give a name to processes. So you can name them by whatever you want. Normally it's an atom. But this is a process. So let's dig a bit more into the primitives that allows you to like handle processes. So how do we create a process? How do we make a process? Well, it's very simple in Erlang. You have a built-in function which is called spawn, generate, which takes 3 arguments, a module name, a function name, and a list of arguments. There I have 2 processes. So let's say that we are process 1 at the top, and we call this function. The only thing we do is to spawn, to create a new process, process 2, which will execute the function which is specified in the arguments. So it will execute the function math, like the function called fact in the module called math with argument 5. So we are creating a process which is executing the factorial of a number. An important concept here is that this spawning operation is asynchronous. So we don't wait for the process to calculate whatever it has to calculate and return back control to the original process. We just create a new process and we get back any very valuable information, which is the process identifier of the newly created process. So you start from process 1, create a new process, and do something else, maybe spawn other processes, while in the meantime, process 2 will execute that function. This creation of processes is extremely cheap. It takes microseconds, and also a process, which is an internal Erlang process, is extremely cheap in terms of memory. One single process takes about 300 words of memory, where a word is like 4 bytes in a 32-bit system and 8 bytes in a 64. And that includes also the heap of the process. And that heap will like shrink and increase according to like your needs. So spawn, a synchronous operation, returns the process identifier of the newly created process. And the process identifier which is returned, it's very important to you because it's the only way you can communicate to another process. The way you communicate to a process is by sending a message to that process. So each Erlang process is equipped with a mailbox where every other process sends messages, and all these messages are piled up in a mailbox in order, and then you consume those messages one at a time. So you have 2 constructs in the language. You have a send and a receive statement. At the top is how you send a message in Erlang. You have 2 processes, process 1 and process 2, and you want to send a message from process 1 to process 2. You can send any valid Erlang term. In this case, I'm sending like a tuple, like with 2 elements. My own, so process 1 is sending this tuple with the first element, which is the process identifier for process 1. I'm calling this built-in function self, which returns the current process identifier, plus a general variable that could contain anything. The operator that I use for sending a message is the bang operator or exclamation mark. So I'm just saying, I'm process 1, I execute that function and say, I want to send a message, self message, to process 2. This is an asynchronous operation, so I send a message and keep doing something else. On the other side, process 2 will execute a receive statement where it will receive messages. And it can match on the kind of messages that you want to receive. So in this case, we have a process 2, if it's executing this statement, will receive messages of this form, like a start message and a stop message, where the first element is the from. So why would you include your own process identifier, so this from field in the message? Well, because the only way you can communicate with another process is by knowing the process identifier. And if process 1 is sending a message to process 2, probably wants a reply back. So one way to share this information, since we don't have shared global variables or shared memory, is to embed that piece of information in the message we send. So it's a bit verbose if you want, but we are including information on who we are, so that probably in this piece of code, process 2 can actually reply back. One important thing is that the receive statement is blocking for process 2. So at some point, process 2 will receive this point, it will enter a receive statement, and at this point will block, so that it will only unblock if one of these patterns will match one of the incoming messages, and then it will proceed. So, okay, we know how to create a process, we know how to send messages and to receive them. Now we look at how a process looks like. What's his life cycle from his infancy to his termination? And this is probably the most important slide of this talk. It's the thing that you should remember. If you can remember a second thing, the first one was, when you think about Erlang, think in terms of processes. And this is how a process looks like in Erlang. I'm representing the life cycle as a state machine, where you start a process, and then you go into a state which is initialization. So imagine that, think about a process like a server. And maybe you are handling writes and reads from a database. You start the server, which will initialize itself. So probably if you're handling with a database, you will connect to the database and then get a connection identifier or something, or you open a file, you initialize your state. Then you go into this giant loop where you start handling requests. Every time you receive a request from a client, you just execute the request and loop again, until someone sends you a stop message, in which case you go to the terminate state, which is basically the opposite of the initialize. It's a cleanup. So before dying, if I open a connection to a database, I close that connection. If I open a file while I'm initializing my state, well, I close that file in the terminate. So let's look at a couple of things. So each block of the state machine corresponds to a function. So what does it mean starting a server? So there is a bit of syntax here. I told you that the syntax is ugly, but I think it's pretty readable. So what happens when you start a server, given some arguments? Well, you just call spawn, because that's how you create a server. So what should the server do? Well, it will execute the function init in the module called server. So that means that all of this code is in the module, which is just, think one module corresponds to an Erlang file, to a text file, which is an aggregate of functions. So this
is probably the server module. It resides on the text file called server.erl, for Erl is the extension for Erlang source code. The function is called init, and we basically forward the arguments that we get in the start, to the init function. So we create a new process which will execute the init function. What this does, it does the do init. So it uses the input arguments to do whatever it wants. For example, given args could contain the file path. So he opens that file path, does something with it, and he returns a state, which is something that we want to keep in memory until we die. So we take that state and we pass it through the loop function. And the loop function is where we handle requests from clients. So this is a complete server. In the loop function, we take this state, and the loop looks like an enormous receive statement. So the server will block there until he receives a message, which in this case can be of two forms: an handle message, or a stop message. If we send a stop message, what we do is we call the terminate function, and we do some cleanup, and we don't loop again. I'm calling stop, it goes to terminate with the existing state, and when you call the terminate, we just clean up, so we probably do the opposite that we do in the do init, and there is no more code to execute, the process will terminate normally. Yes? No, in this case, we can say we are not sending the from. So you can send any type of message. In this case, I'm sending is like an internal protocol that I'm using for this example. So these are atoms in Erlang. If you're familiar with atoms, it's defined as a constant literal. Is a variable whose value is the name itself. So it's just a label, if you want. So in this case, we just send a label stop. And in this case, we send a tuple of two elements where handle, just say, this is an handle message, something that I want to call handle for, could be anything else. And this is the message itself. So we take the message. So if we get an handle message, we execute the function, which we call handle. It's not implemented here, but it could be whatever, read to the database. So for example, if this was a database server, you would expect two messages, instead of handle, you would have a read something or a write something. And then you would call read or write. So the trick is, here, Erlang is a functional language. And what we do here is after we handle our own messages, eventually modifying the state. So we have the initial state, which is passing the loop. We take the state, we call the handle function, and we eventually get back a new state, an updated version of the state. And the trick is that we recursively call the loop function with the new version of the state. This is like recursion. Bad, right? Because it's dangerous. But if you pay attention to this, you should notice that this is actually a tail recursive function. It's recursive, but it's tail recursive. So what we do is, whenever we have a recursive call, it's always at the end. It's the very last thing that we do. So these functions are optimized so that basically we use recursion to keep the process alive, so that we can handle one message and then loop again, so we can handle the next message. But this will never cause the stack to grow. So the memory which is used by this process will get constant. It doesn't matter how long this stays for. So, yeah, a loop is a receive. We handle messages, we return a new state, and then we loop again with a new state. If we are done with it, we send a stop message, in which case we just clean up whatever we had using our internal state, and then we don't loop again, and the server process will just die. So there are two kinds of terminations for processes. One is normal termination, so we are done with whatever we want to do. So we handled a bunch of messages, then we get a stop, we terminate, fine. This is normal termination. But we also have the concept of abnormal termination, which means somewhere here, maybe in the handle function, we have a bug. We have a problem, so we crash. So what happens there? Like, Erlang is one of those few languages where crashing is okay, is acceptable. And the reason why it's acceptable is because we have something called link. Given two processes, process A and process B, we can link one process to another process. The link is a bidirectional channel, so it doesn't matter if A is linking to B or B is linking to A. You link by calling the link function, given another process identifier. So in this case, process A is linking to process B, but it could be the opposite. It would not change anything. There is also like monodirectional links, which I'm not covering, but this is a bidirectional link. So what is a link for? Why do we link processes? Well, because a link is a channel for an exit signal. We have three processes, just to give you an example, A, B, and C. And A is linked to B, and B is linked to C. Process A crashes, maybe because I have a type error in my handle function. We don't have types, so it's really easy to get these mistakes. And then, yeah, we die. So for us, it's not a big problem, because we can recover from that situation. Like, it's acceptable to die. So when process A dies, it forwards an exit signal saying, I'm process A, I'm exiting, I'm dying for this exact reason. And it gives you the stack trace, for example, for why I'm dying. Maybe I'm calling plus between an integer and a string. So process B, by default, will receive this message, this exit signal, and it will die as well. And it will forward this to all the linked processes. Since B was linked to C, it will forward the message saying, hey, I'm process B, and I'm dying because of this reason. And this will cause the other process to die as well. Now, the nice thing about having processes is that we have the ability of taking a huge task, splitting that into small things, and have a single process executing like a very small piece of the code in a very natural way for a developer to understand. But now, if a small bug in a process can provoke like termination of all the processes in our system, that doesn't seem the right approach. So what we do is that we can extend this, and we can flag a process to have some kind of different behavior. So we say that we can trap exit signals. So let's look at the same example once again. We have three processes, A, B, and C. This time, process B, the one with the two circles, it's calling this function. It's a built-in function which is used to set, like every process has a bunch of flags. One of these flags is called trap exit, and we set it to true. So what we are saying is process B should not have the default behavior of dying whenever it receives an exit signals from a linked process. What B should do instead is to, well, so process A crashes, an exit signal is propagated through the link between A and B. Process B has this flag enabled, so it's trapping exit. What it does, it converts the exit signal into a message, which is received in the mailbox together with the other messages. So it will not die, and if it is in a loop, when we have the receive statement, it will basically handle the case where this, like, we have a receive with an exit signal saying that process A crashed. For example, I mean, we use these languages for real. Like, I work for like Klarna right now, where it's a banking system, so we handle money. So you understand, like, when you say to a manager, yeah, crashing is okay, well, if they're from the banking system, they might have a very strong opinion on that. So what you do there is, well, say that this is a transaction. There is a mistake in the code. So the only sensible thing you can do is to actually die. You can't do too much. Like, there is a bug, so you need to work on that. What you can do is that, well, someone else will be notified, and then he will react to this message. So if process A was crashing because of a type conversion, fine, that transaction will fail, of course. The rest of the system will not be affected. Maybe it's like a user which is using a weird typeset. So we didn't handle that case. So it will crash. It will notify another process which will do something, for example, log, and send to the developers like a message like, we don't know how to handle this. And the system will keep alive and stay alive and continue to work as usual. And then in your mailbox, your developer mailbox, you get, oh, there is a crash. I know how to solve this. And then the thing that you can do is basically like, well, use another nice feature of Erlang, which is hot code swapping. So you can basically replace the code which process A is executing with a new version, with a bug which is fixed, without bringing down the system. So if we relook at this, what happens is, if PDA is crashing, the reason of the crash is sent through the link. Process B will convert this exit signal as a message. We will receive it, and that's it. Process C will not be affected by this. So we stop propagating the exit signal. Does this remind you of something? This is the same picture, just rotated a bit. So if like this looks more familiar, we can identify actually two layers where the processes which are trapping exits are called supervisors. And they don't do a lot of code. They don't execute a lot of code. The only thing they do is to monitor other processes, which are called workers. So the workers do the real stuff. They execute the code which is written by developers. But these workers, the leaf of the tree, you can nest this thing so you can have like a complete supervision tree. When you have a problem with the workers, well, one worker will crash. It will notify the supervisor, which maybe will just restart the process. And you can do like a lot of other nice things with Erlang. So where would you start if you're interested in Erlang? Well, the obvious entry point is erlang.org. There is the official homepage. You can find all the documentation and everything there. I'll put the slides on the GitHub, so don't worry about that. Erlang is open source. It's available on GitHub. So if you want to look at the source, you want to compile from source, you can just go to github.com, Erlang OTP. If you prefer a binary, like for Windows or Mac, there are pre-compiled packages at Erlang Solutions website. The best way to learn about Erlang, there is a free online book which is called Learn You Some Erlang. Basically a port of Learn You Some Haskell for Great Good, which is nice, but it's pretty long, but it's free. And then the two books which I would suggest is Erlang Programming for the basics, so all of this stuff. And then we have a framework which is called OTP, which is what you use for real, like a bunch of libraries built on top of Erlang, and that's called Erlang and OTP in Action, and that's a beautiful book. By chapter, I think 6 or 7, you will implement a completely like client-server architecture with cache and a lot of things and chat servers. It's nice. The suggestion is don't start with Erlang and OTP in Action because it could be like a bit heavy. So if you follow this order, Erlang programming first and then OTP in Action next, it's a good start. And I want to leave a bit of time for questions as well. And well, you can reach me. I'm Roberto Aloi everywhere, so GitHub, Twitter, whatever. You just Google me. Any questions? Yes.
where there is a workflow. Yeah. Okay, so here spawn is the only built-in that we are seeing in this code. Am I correct or not? So we have to think to this code as executed. Well, it's seen sequentially, but we have to think about functional invocation of one thing into the other. That's okay? Okay. It was not a question.
I'm not sure what the question was like.
I was trying to understand what is the program that you are writing, what is the built-in that you are using to instantiate processes and messages.
So this is a process skeleton. So this is using the built-in primitives. So we have a spawn to generate a process. We have a receive statement to receive a message from a mailbox once at a time. There is not shown the stop function, which would use the other built-in operation, which is the bang, which is like just sending stop to the PID. In practice, all of this is provided by libraries, so you don't write this. The only thing you would write in a real Erlang application is this function. So you don't have the risk of a developer writing a loop function which is not tail recursive and then dying miserably because it runs out of memory after a while. So, of course, I cannot cover that, but we have something called a gen server. It's a generic server, which does exactly that. So actually, what the gen server does is it implements all the boilerplate, which is this. We have way more things to cover, like timeouts, like order of messages, messages from processes which we don't know about or we don't care about, hot code loading. So the only thing you do in practice is to write your handle function, where you just say, well, I'm a server. Every time I receive a message, given this state, do something else with that message and provide a new state. The do init function, that's specific to your application, so you are required to implement that, and the cleanup function. And possibly like a code change function, which in case of hot code upgrade, we can just send a message to a process saying, right now, this is the new version of the code that I would like you to run. Please run it. And then you have a code change callback function, which you implement, which tells how to swap between the old state and the new state. So like converting it. Any other questions? Yes.
Compared to other functional languages, okay, Erlang gives you processes more scalable horizontally. It's more with these kind of processes with workers and supervisor. It's good for this kind of distributed system. But what about the expressivity of the language? When you have a very difficult problem to solve and you don't know how to solve because an imperative language is not good, doesn't fit with the problem. For example, compared to Haskell or other languages, functional.
So this is actually one of the reasons why I like Erlang, because with the other languages, like with an imperative or object-oriented programming language, you focus on the algorithm, right? Like I have this problem and I want to solve that. So Erlang, the main part where it helps is not to write the, I don't know, like mathematical functions to convert some input in some other input. Like you don't gain anything from Erlang using that. You could use anything else. And in fact, Erlang can actually talk to other languages. So you could implement your stuff in Java or C and then just execute that code. What is nice about Erlang is that whenever you have a problem, the first thing you do is, instead of writing the code, you start modeling the problem in terms of processes, sequence diagrams. Like, oh, I'm here, I receive, like, you normally use it for writing servers. So say that you're writing a web server. Like, okay, I have a client which connects and send a message to this process, and when we receive this process, and we do this, and then we return back this. So I find myself to spend a lot of time in writing pen and paper and to actually understand the problem I'm trying to solve, which is also nice because you can talk to managers and people, like non-technical people, the ones that are giving you the specifications, and before implementing something, you just say, is this okay? Is this how you want this to work? And the other thing is, in Erlang, it's natural to think about failure. Because the next step is, okay, I have these processes, what happens if I die here? What happens if the connections to the database breaks? And in other languages, you don't do this. You focus on the problem. But I mean, this is obviously personal, so this is why I prefer Erlang. And again, I don't want to compare Erlang with other functional programming languages, because if you're looking for a functional programming language, just use Haskell. Like, there is no reason why you should use Erlang. Erlang is a concurrent language, which happens to be functional. So you have pros and cons. Yes.
How do you see this actor-based programming model compared to the other state, which is now also very popular, using promises and futures?
I don't really know. I think a lot of programming languages which are implementing these concepts are kind of stealing ideas from Erlang, which I think is a great thing. So personally, like, I don't see a competition. I would like to see like the overall goal, which is combining this concept, thinking in terms of processes, for example. And if another programming language comes up with like a model which is pretty different, but it steals what is good from Erlang, I don't have a problem with that. I'm actually very good, like, Go stolen something from Erlang as well, like, and other programming languages do the same. Erlang did exactly the same. I mean, the syntax is like Prolog based. When they invented Erlang, they just took all the existing programming languages and they say like, well, let's put them together, like, let's see what we can use from one or the other, and then they come out with something completely new. So a lot of the things are ugly, but the main principles are actually correct. And I wish other programming languages could pick this. And then I would be really happy to swap from Erlang to something else. But I don't know if that answered to your question, but it's, I mean, it's, yeah. Yes.
I know that it exists an optional type checker for Erlang, which is Dialyzer, if I'm correct. And so if Erlang doesn't need a type system, why has it been invented, and when it is used and how?
So the fact that you don't have a dynamic, like that you have a dynamic typed language, of course, is more error prone. This is like weird.
Yeah, I'll just use this one. So yes, in Erlang, like, just to give a bit of context to everyone, you don't see types here, right? So this is really error prone. You could write a function and then maybe you don't know how to handle with that specific type, in which case it would generate a crash. We have something which is called Dialyzer, where you basically annotate your function with type definitions. So you say, well, this function will take this kind of like input, this is a string, and it will return an integer. So you say, well, if this function takes an integer and converts to a string, and then this other function does the opposite. If Dialyzer basically is a tool that you run at compile time, it will check all the inconsistencies and it will warn you, like, there is an error here. In like 50% of the cases, an error in the specifications. Maybe like the code is correct, but you wrote your specification badly. Or in other cases, he's actually right and he finds a lot of bugs. It's really helpful because I think Erlang is one of these languages where if you don't have type, of course you have less safety, but you have more speed. Like, you can you can write your code like, I mean, you don't have to put the type definitions there. So you can be like quicker when you write. You can have like more dynamic things. You have features like hot code swapping, which are available, which would be like really tricky to get in a statically typed language. But then if you have this check, like where you specify the types, that helps you. The real answer is that I still see Dialyzer as an overhead, because it's not the truth. It's like documenting the code that you're writing, and you make mistakes there. So I always use Dialyzer, but sometimes I feel it's like it's a pain that you need to do that yourself.
That's why we have type inference in most languages.
Yes.
Most platforms.
Yes, which would be nice to have. Yes.
A question about how you proceed to write the processes. I found very difficult to project software multiprocess, and test software multiprocess. So if I have a lot of process spread in a lot of machine, I found very difficult to handle all the cases, write tests for all the cases, or I have to test on the real. So I cannot test on the real. And in many cases, I have a lot of problem in testing software multiprocess. So if this way of writing have a so high level of multiprocessing, it can be very difficult to test. I don't know how to test it.
So did you try to do this with Erlang processes or with processes in general? So the main advantage you have is that you don't have global variables or shared memory. So every single process is completely isolated, which means you can mock everything else and just focus on testing one single process. But then you want to test the combination of the two. We have one beautiful tool which is called Quick Check, and which comes with another sub-tool which is called Pulse. So what it does is, for example, you can model your system as a state machine. And you have you give a sequence of possible events that happen. And what QuickChat does, it creates thousands of possible inputs, and it will try your system until something breaks. And the beautiful thing there is, whenever something breaks, it has a feature which is called shrinking. So it will take the failing case and it will reduce it to the minimum. So it will spend a bit of time, a couple of seconds or even minutes sometimes, and it will go and show you the minimal case which goes a problem. And you can do that in concurrency as well. So if you have, for example, several processes interacting, what it does, it calculates all the possible interleavings, and it will try all the combinations. And that's a beautiful tool when you want to test something like this. We have some tooling for that.
So you project the software to be isolated as much as possible, and when it's not, you try with the sequence.
I mean, when you have a system, what we do is you split the big problem into small things, and then you give them to your processes. So a process will do a very simple thing, and then again you test both consider that as a unit test for the process, where you test just that process. What happens if I receive this kind of message, possibly dynamically generating the input with something like Quick Check. So you pass a bunch of, I don't know, you say execute, send a message with lists of dynamic size going from 0 to 2000, and every element of the list will be a string which goes from empty sequence of characters to whatever. And then at some point you will find something which is breaking. And the same for processes. But I mean, we have We have nice tooling. We also have something called common test, which helps you to test distributed systems where you have different machines. One of the beautiful things is if you have like a distributed system, like 3 machines, heterogeneous, you can actually like execute something on the machines, and you even have cover reports. Like you can actually see the source code with like how many times you executed this line of code, which is aggregated over a distributed system. So if I have like several nodes, they can all contribute to the same code coverage, which is nice.
Okay, we have time for just one more short question.
When you have ton of processes, I assume that you have processes that are on the same core, on the same CPU, or on different servers. How is it managed, the fact that when you send messages, obviously the time it takes to send messages change? Is it something that is taken care by the runtime to, I don't know, moving processing near other processing they are talking to? Do you have to handle that by hand? How does it work, more or less?
So it's completely transparent to the user. You don't do this because you're not supposed to do this. So the way it works is the Erlang comes with like a virtual machine, like the Erlang virtual machine, which is similar to the JVM, if you want. So you have 1 thread per scheduler that you have in your machine by default. So if you're an 8-core system, you will get like 8 processes there, connecting the operating system with the virtual machine. And then for each scheduler you get, so for each thread you get like an internal scheduler. And that end is beautifully like handling everything for you. So you have like a run queue for each scheduler, and then you basically like, you don't care about this, so you just create processes and you let the virtual machine to allocate the resources as much as possible. And then there you have like clever algorithms for splitting the like moving stuff from one scheduler to another, or you have also like projects or research projects for locality between processes. So what happens if they are local or not? Of course, like if the process is spawned remotely on a different machine when there is like network, that's more expensive. But in that case, you do it explicitly. So you say, I want to create this process on that machine. But it's like normally, like when you spawn a process, is on your node. And then you can monitor stuff coming from other nodes as well. So it's nice.